Thanks very much. It's very nice to be here. So I'm going to give you a very quick summary of work that's been taking place over the last couple of years on 2+1 dimensional gauge theories and their infrared dynamics. So even though this is the high energy session, it's not going to be about high energy. It's going to be about deep, low energy. So let me start. So I'll explain some recent non-perturbative results, conjectures, dualities, and things like that concerning the dynamics of 2+1 dimensional gauge theories. Now, 2+1 dimensional gauge theories are quite interesting because they display phases that have no obvious counterpart in 3+1 dimensions, which is a subject that's more traditionally associated to particle physics. So just to set up the terminology, there will be three kinds of phases that we will encounter, though there are more complicated options that will not appear in this talk, but appear in various papers. So trivially gapped means that you have a trivial vacuum, which is nearly a direct product of the sites, and that there is a gap. Then there is the option of having a topological field theory. Let me see how that works. So then there is the option of a topological field theory, which means that there are no actual massless excitations, but there is a non-trivial response to putting the theory in curved space. Then we will see various examples when there are actually massless particles, accompanied or not accompanied by topological field theories. There are several options there. So these are roughly speaking the options. And I will consider, in the first part of the talk, I'll consider two examples in parallel, and then I'll discuss slightly more recent examples that appeared, that are still in progress or have just appeared in the literature. So I'll consider in parallel two models. One is SUN gauge theory coupled to an adjoint Majorana fermion. And this theory is labeled by, this theory is going to be, the dynamics of this theory is going to be a function of the mass and some Chern-Simons level. And this theory I'll call adjoint QCD, just because that's how we call the analogous theory in 3+1 dimensions. I'll discuss the phases, dynamics, and so on. And then I'll also discuss in parallel SUN gauge theory coupled to NF fundamental quarks. So fermions in the fundamental representation of SUN. And that again is going to be a function of some Chern-Simons level and mass. So that's what I'm going to do in the first part of the talk. And in the second part, I'll discuss briefly more complicated or more rich examples that led to various new possibilities that did not occur in these two examples. But these are the simplest two examples. So first, these theories are of course strongly coupled in the infrared in various cases, and you cannot solve them analytically. So you have to understand. So the strategy is to first understand in extreme detail and very precisely all the weakly coupled limits that we definitely know exist, and we can establish them mathematically. And then we would like to patch up the phase diagram, so to speak, of this model by using all the constraints in our toolbox, like anomalies, consistency of phase diagrams, contact terms that I'll mention briefly perhaps, and many others. So the idea is to first go after the weakly coupled limits, get them straight, and then push on to the strongly coupled regimes, and where you make conjectures essentially. But these conjectures are then going to be supported by a lot of consistency conditions. So one strong non-perturbative consistency condition that is very familiar in high energy physics from the study of 3+1 dimensional models is anomaly matching, so anomaly matching in 3+1 dimensions is particularly powerful because there are continuous anomalies. But in 2+1 dimensions, or the anomalies are discrete, meaning all the group cohomologies are discrete, and so a 't Hooft anomaly matching may appear less constraining. But from experience working in this field, it turns out that it's not really so. There are many discrete anomalies that will appear in this talk, though I will not explain anything in detail, obviously, since I just have 25 minutes. But one important discrete anomaly that will be used is in theories with time reversal symmetry, you can try to put them on unorientable surfaces or unorientable spaces, and there is a certain phase that's valued in Z16 that's computable and very constrained on the infrared dynamics. That's one. Another anomaly that has played an important role in the derivation of these proposals and conjectures is a mixed anomaly between time reversal and some U1, if the symmetry group includes some, something like particle number conservation and time reversal symmetry. There are one-form symmetries, various other anomalies for global symmetries, and we use all of them to test these conjectures. So it's not really true that there are no significant constraints in 2 + 1 dimensions, since these discrete anomalies are quite constrained. Okay, so let's start from our writing down the Lagrangian for our 2 examples. So unlike in condensed matter physics, where we start from a lattice, here I start from a completely well-defined, super-normalizable quantum field theory, meaning that the conjectures that we're going to make here are in principle testable on the lattice. There is Wilson's lattice or variations thereof, and in principle these conjectures are testable. And they concern with an ultraviolet finite quantum field theory. So the Lagrangian includes a kinetic term for the gauge field, a Chern-Simons coupling with some integer or a half integer k, depending on various things that I'll soon say. And then this gauge field is coupled to some matter fields. And these matter fields in these 2 theories that I'm going to discuss in parallel are respectively in the adjoint representation or in the fundamental representations, and then we have n(f) copies of them. So we either have n(f) copies of the fundamental representation, or we have 1 copy of the adjoint representation. So these 2 theories have somewhat similar strategies of attacking the question of their non-perturbative dynamics. So I'll discuss them in parallel.
You always assume k is non-zero.
And I'll also allow k to be 0. I'll explore the dynamics of this theory as a function of k and the mass, and I'll provide conjectures for the answer for any k and n. In some cases, these conjectures are testable and provable. In some cases, they depend on some lattice computations that are yet to be done. So the consistency of this model requires, of course, that this is properly quantized. Otherwise, this is not a well-defined functional for the gauge field. So just for the record, in the adjoint case, if the rank of the group is odd, then k has to be a half integer. And in the QCD3 case, if the number of copies of the fundamental representation is odd, then k has to be a half integer. Now, the adjoint QCD model has no global symmetries whatsoever, except when this k vanishes and n is even when there is a time reversal symmetry, and we will use that very importantly soon. While the model of QCD3 has an UNF symmetry that rotates these NF flavors among each other, where the UNF consists of SUNF and the U1 baryon symmetry. Now, the adjoint model, while it does not have ordinary zero-form symmetries, it has a one-form symmetry, since there are no propagating fundamental representations. The Wilson lines for the fundamental representation and any power of it, mod n, are important observables, which can be thought of as order parameters for a one-form symmetry, using the terminology of Kapustin-Seiberg and Gallardo-Kapustin-Seiberg with it. And that also has various anomalies, and it's an interesting symmetry of the theory. Now, of course, in condensed matter physics, one never has exact one-form symmetry, but that doesn't matter, because once we establish the infrared dynamics of this model, since it's going to include some topological phases, they're going to persist even when there are heavy fundamental quarks. So if you can tune your lattice system such that there is a certain gap or a certain hierarchy between the adjoint representation and some fundamental representation, say, then the lessons that we learn here would still be true. So, quantum field theory is generally useful when there are hierarchies of scales in the lattice model. So the first limit that's very easy to analyze, and one can get everything straight in this limit, and there are no conjectures, is the limit where the masses of these representations are very large. So these fermions are very massive. And obviously, when these fermions are very massive, they're not going to make a huge impact on long-distance physics, since they're so massive. So it's not completely correct to just erase the fermions altogether when they're massive, which is what you might have thought to do, because there is a famous non-decoupling effect that was first established by Redlich and Semenoff in the 80s in the papers that came out almost at the same time. And what Redlich and Niemi and Semenoff showed was that even for very massive fermions, if you try to get rid of them, you have to slightly shift the Chern-Simons level. But other than that, you can erase them from the Lagrangian. So this is called the non-decoupling effect in high energy physics. That even when you have very, very heavy particles, you cannot quite just erase them. There is a certain trace that they leave on the infrared physics. So you have to shift the K, this K appropriately, like this. It depends on the sign of this mass. And you have to keep track of that. So this is one weak coupling limit. Another weak coupling limit is when the Chern-Simons level K is huge. So one weak coupling limit is when the mass is huge. Another weak coupling limit is when K is huge. Because when K is huge, as you probably know, the Chern-Simons term gives a mass to the gauge field. So when K is huge, you can erase the gauge field rather than erase the fermions. So erasing the gauge field is also very helpful because then the theory becomes essentially trivial. So this is another weakly coupled limit. And in more detail, the gauge field now has mass kg squared. And if kg squared is much bigger than g squared n, then the gauge interactions are very weak. And we can solve this model in this limit rigorously. And this was basically, I think this was essentially done first by Appelquist and his collaborators. So the answer in this limit is that, well, let's say we take k, which is 1,000, and then we scan over the masses, right? So we're still allowed to scan the masses. So what Appelquist and collaborators have found is that essentially in this limit there is always a second order transition, which I'll explain. So at some special value of the mass, which is very close to 0, there is a conformal field theory, which is weakly coupled. Now, so just to conclude, if you fix k to be whatever you want, and you take the mass to be huge, you always get a topological field theory, because you can erase the fermion, you have to shift k, and you get a topological field theory, which is of the Chern-Simons type. And another thing is that if you fix the mass to be anything you like, and you take k to be very large, it's always weakly coupled. It can be either in a topological field theory phase or some weakly coupled conformal field theory phase. So these two limits are very well understood. So let me just say it more precisely with a diagram. So this is the adjoint QCD case. The adjoint QCD case has two parameters, which are the mass and k. And k is essentially either an integer or a half integer, so we can just fix it. So let's fix k to be some number which is huge. It's much, much bigger than n, where n is the rank of the group. And then we draw the phase diagram as a function of the mass, which is the only continuous parameter. So what we learned from these old computations in the 80s is that first, at very large mass and very small mass, very large positive mass or very large negative mass, there is a topological field theory. But the topological field theory here and the topological field theory here are not the same because of this non-decoupling effect. So there must be some phase transition. And you can prove it non-perturbatively. There must be a phase transition. Now there is an interesting question of whether this phase transition is first order or second order, whether there are multiple phase transitions. And Appelquist and his collaborators found the answer in the 80s, which is that if k is very, very large, there is a single second order transition which is weakly coupled. And that's it. So for huge k, we know the answer. Yes?
Is that m equals 0?
The question of where exactly the phase transition is located is slightly scheme dependent, since, as I said, in this model there are no global symmetries. So the point m equals 0 is not special by any means when k is non-zero, and here k is large. So it's slightly scheme dependent, but since it's a very weakly coupled model, you can say that m is 0. It's essentially 0. Since it's weak coupling and you can solve the model, it's essentially at m equals 0. The scheme ambiguity is very small in this model. So where there are h bars, and h bar is 1 over k. So you can make a determination of m quite precisely. The same is true for QCD. For QCD, there are again two distinct topological field theories at large positive m and large negative m. And again, for the same reason, there is a second order phase transition which can be understood in detail. There is a conformal field theory for a very large k. So the question is obviously what happens as we lower k? What happens to these two phase diagrams as we lower k? Lowering k is like increasing h bar. The theory becomes increasingly more strongly coupled, and one can do less and less controlled computations. So the question essentially is what happens as we lower k. And in fact, unlike in 3 + 1 dimensions, where we know very little about such questions, here there is a more or less concrete answer. Various arguments, self-consistency of the picture that I'm going to tell you, and so on, imply that the critical values of k, where the picture would dramatically change, are n/2 in the adjoint case and an f/2 in the flavor in the QCD3 case. So we more or less know what values of k this picture might dramatically change, and you'll see why how these values arise. So there are some preliminary comments here that I wanted to make, just to give you a hint of why these are possibly the correct answers. So comment number 1 is that the adjoint QCD model has one property that I did not yet mention, which is that for some very special tuned value of the mass, it has 2 supercharges, so a little bit of supersymmetry in 2 + 1 dimensions. And at that special point, at that special value of the mass, which is given here, Witten has found that this value n/2 is very important. Okay, so that appeared in the computations that Witten did in the early 2000s for the Witten index, and so this is one indication that this is an important number, n/2. For the QCD3 case, there has been, as you know, a lot of work on Chern-Simons method dualities. And if you look at the details of those dualities, which were worked out by Aharoni and Minwala, these dualities do not make sense at k, which is smaller than an f/2. So that's an indication that an f/2 is an important, critical, maybe a boundary of the phase diagram in some sense. So these are 2 indications that something might take place at those values. So obviously to describe, so my assumption is going to be that these 2 pictures remain correct, not just at very large k, but all the way down to n/2 and n f/2. Now, to say something concrete about what happens at lower k is, of course, beyond the realm of perturbation theory with coupling techniques. We have to make conjectures. And that's the content of the papers, with several papers with Nari Seiberg, Jaume Gomes, and Nari Seiberg, that from the last couple of years, and several other papers that I did not mention, but I'll mention soon. So let me just present the conjectures, and I'll briefly say why these conjectures make sense. It's actually useful to start from the most weakly coupled case, which is when k vanishes. K vanishes is like the smallest value of k that is permissible, and that's like the most strongly coupled regime, and one can work one's way out once one has a conjecture about that. So it's useful to start from the massless theory at k = 0, which also has time reversal symmetry. So the added value of starting at that special strongly coupled case is that there is time reversal symmetry, there is an anomaly that one can try to match. So let me just present the conjecture that we've proposed for adjoint QCD. So what we've proposed is that SUN coupled to an adjoint fermion at vanishing k and vanishing mass flows to a new topological field theory. So this topological field theory is not the same as the topological field theories that appear here in the weakly coupled phases. It's an emergent gauge field, if you like. There is an emergent topological field theory, so to speak. So there is an emergent topological field theory and a massless Majorana fermion, which is uncharged, completely decoupled massless Majorana cone. So this is the conjecture for the massless k = 0 theory. This conjecture satisfies quite miraculously all these consistency checks, because this particular topological field theory has an anti-unitary symmetry, which can be associated to the original time reversal symmetry in the ultraviolet. And one can compute its indicator, or the new anomaly. And together with this massless Majorana fermion, it works for every n. In addition, this conjecture makes sense vis-a-vis the supersymmetry that I mentioned. This model has 2 supercharges, and there were arguments in the past by Witten that there must be a massless Majorana cone at that point. So that makes sense. In addition, this conjecture satisfies the one-form symmetry anomalies. As I said, there is a one-form symmetry in this model. and and one can just verify that it has the right anomalies. And as I said, the time reversal anomaly is matched. So, long story short, this conjecture passes many consistency checks, and so the idea is that there is an emergent time reversal invariant topological field theory in the infrared of this model. One surprising thing about this conjecture is that it means that adjoint QCD is not confining, unlike in 3+1 dimensions. In 3+1 dimensions, adjoint QCD confines. But here, what we're saying is that adjoint QCD deconfines, and it leads to anyons, which form a complicated non-abelian fusion category. So in this respect, you might think that 2+1 dimensional adjoint QCD is perhaps analogous to 1+1 dimensional adjoint QCD, which also deconfines for dynamical reasons.
So there are these anyons as massive particles that compute the masses in principle? Or?
So these anyons, they represent the world lines of heavy quarks.
So you have to add them separately. They're not in this particular theory, the way you define it, does it have these heavy quarks?
That's right. The theory doesn't have such heavy quarks, which are dynamical, but it has Wilson lines in the ultraviolet. And in the infrared, this Wilson line satisfies some fusion rules.
Sure.
And physically, what it means is that if you were to introduce a heavy particle, then in the infrared, this particle would become an anion. But it means that the theory deconfines, and that the fundamental quarks, which are Pearl particles, become anyons. So this is quite different from 3+1 dimensions, and in fact, it's a little bit more analogous to 1+1 dimensions, rather than 3+1 dimensions. So let me just, now this is the phase diagram for any k. I'm now extending it quickly to any k. I'm not explaining how and why. I'm just giving you a loose picture since I have so little time. So the idea is that for a small k, below this critical value of n over 2, these two topological filters are always there. These two topological filters can be established by decoupling these quarks when they're very massive. There must be some phase transition. And for large k, we argue that there is a single second order phase transition. However, for small k, the picture is that there are two phase transitions, not one, and that there is a new quantum phase where there is an emergent topological field theory. So the previous discussion was about k equals 0 and about m equals 0, which is this blue dot. But in general, this blue dot is surrounded by some region where there is a quantum phase. So we call these things quantum phases because the fact that there is such a region in parameter space cannot be established by perturbation theory. It's a strongly coupled non-perturbative effect, but we've conjectured that it exists because it made so much sense with many consistency checks. We computed the whole conductivity, anomalies, and everything just works, and it fits into a bigger picture of duality. So it's a very compelling conjecture. Yeah.
So this is certainly a consistent picture, but could there be a direct transition with a strongly coupled CFT? Could you rule that out?
You're asking if I could rule out, for instance, this kind of picture?
Yeah.
No. In this business, it's hard to rule out something, especially if it concerns a strongly coupled conformal field theory that could saturate all the anomalies. We don't know. But amazingly, there is a scenario which does not involve a strongly coupled conformal field theory, but rather just a topological field theory and some atlas Majorana cone that satisfies all the constraints. And it's self-consistent. It leads to some dualities which are consistent. And
Yeah, I get it.
yeah.
So this is certainly consistent.
This is a consistent scenario that looks very compelling. Yeah.
Can you solve the CFT in some limit? This particular.
So what we cannot prove that this is really second order. Unlike the large K computations of Appelquist, we cannot really prove that this is second order. However, we have a dual description for this conformal field theory that I'll mention in a second. And that dual description is another conformal filter, is another adjoint QCD model in this regime of large K. So by using self-consistency, it should have a single second order phase transition. That's not, of course, that's not a proof, but, and so the answer in short is no. We cannot compute the critical exponents of this conformal field theory, but we can approximate them.
Do you imply those CFT have only single relevant operator?
Yes, this picture relies on the idea that these conformal field theories have a single relevant operator.
There is some evidence for that.
Yeah, these are the same CFTs that we've seen. So the dual conformal field theory, that transition is exactly of this type, and this is supposed to have a single relevant operator. Now, if you have seen Seiberg-Witten theory, you might be struck with the similarity. In Seiberg-Witten theory, there are two special points, which are called the dione and monopole point, and they're mutually non-local. So this is a little bit similar. We have a single model, but it has two transitions with two mutually non-local dual descriptions and a quantum phase. So that's very similar to the U-plane of Seiberg-Witten theory, though it's not the same. So this is the dual description. So this conformal field theory has a dual description with this kind of model. So now it's not an SU gauge theory, it's a U gauge theory with some funny levels and a different rank, but that's supposed to describe this transition. So in other words, this quantum phase is non-perturbative in the original variables, but in the variables of this conformal field theory, it's perturbative. Now, a similar story takes place for QCD3, but here we have Nambu-Goldstone bosons in the quantum phase. So here one postulates a new symmetry breaking pattern. Let me just, I'm running out of time. I just want to jump to, here there are consistency checks, some of which are going to come out. But this is the point. The point is that, that for k smaller than NF over 2, the main part of the main point is that there is a quantum phase with a symmetry breaking phenomenon. It's not chiral symmetry, but there is some symmetry breaking. And this is the formula. So the original UNF symmetry that rotates the NF quarks for sufficiently small k where the theory becomes strongly coupled is broken spontaneously for sufficiently small masses. And this is the symmetry breaking pattern. And amusingly, it depends on k. So the Chern-Simons level enters into the symmetry breaking pattern. And so in diagrams, this is what you get. It's a very similar picture. That's why I'm presenting these two models back to back. There is a topological field theory here, another topological field theory here. There must be at least one transition because they are distinct. But in fact, we postulated two transitions, a quantum phase and a coset of Nambu-Goldstone bosons in between, which depends on k. So the dependence on k is through the coset, and the dependence on n is through these topological field theories and through a certain Wilson-Mino term that we wrote a paper about with Dan Fried and Nari Seiberg. And again, there is a dual description for this conformal field theory, and I've given some details about it here. In particular, I wanted to mention some work of Andreas Karch, who is here, and also some upcoming work by this group, who gave a very compelling interpretation of where this magnetic group comes from, of what is the meaning of this dual group. This is at least to me, this was a very compelling interpretation, and this is going to come out soon. Also, there are lattice studies, 2+1 dimensional Wilson lattice studies by Kartik and Narayanan, which indicate that indeed such a condensate develops. So there are two topics that I want to finish with, which is, do we really know that this is a conformal field theory? At least n small k. Do we really know that these transitions here are conformal field theories? And the second topic is this idea that there is always strong weak duality, which allows you to jump into the quantum phase using weakly coupled variables in some dual description. Is this idea general? So for the first question of whether it's a second order or first order transition, actually recently there was a paper with Adi Armani, Thomas Dumitrescu, who is here, and Guido Festuccia, where we essentially proved that at least for large rank, these transitions are first order. And nobody has yet found a mistake, though I hope the paper has a mistake, but nobody has found one. And in fact, not only that nobody has found a mistake, Ofer Aharoni managed to generalize our results to even finite small k over n. So it's even worse. Many of these transitions are first order, at least for large enough rank. And in fact, this seems like it contradicts the Chern-Simons matter duality literature, which applies at finite k over n, but it doesn't. Because we've argued that once you've had the Yang-Mills term, the RG trajectory just deflects, and it's like a type 1 superconductor. You just never hit the fixed point that Shiraz Minwala and Ofer Aharoni found. So it seems that there is a long story that has not been developed completely yet. It's mostly in progress. But many of these transitions, at least at large n, are probably first order. This is the bad news. The good news is that this analysis at large n, we were actually able to prove essentially rigorously that these cosets exist. So the takeaway message is that these phase transitions perhaps are not universal. Maybe they're not second order in all cases. But these quantum phases, which is the most interesting part for condensed matter physics, are robust. The quantum phases exist, even at large n, where we could prove that they exist. The last point is the question of whether this idea that there is a that there is a weakly coupled dual description that allows you to jump into the quantum phase, whether this idea is general. So for a long time, with various collaborators and many groups, several other groups, people have been interested in understanding SUN with two adjoint Majorana fermions, because this model is a little analogous to some work in 3+1 dimensions by many recent papers, some of which are here. And we couldn't find the right answer for SUN with two adjoint fermions. It seemed like we could never make a reasonable guess for the quantum phase or a dual description. But recently, my student found the answer, Chang-Ha Choi. He made a breakthrough, and he found the answer. And his answer is a little bit more complicated, so I try to draw it here. I'll try to explain what this picture means in half a minute, and then I'm done. So what he essentially found is that sometimes the dual description at this transition that leads to the quantum phase is not weakly coupled, it's strongly coupled. And there is like a duality chain where you follow these lines until you get to a weakly coupled duality node. And then you can do some computations and reverse back and get the dual description in the quantum phase. So my student was able to solve this model of SUN, solved by means to find a reasonable conjecture for the quantum phases. The conjecture is very non-trivial, and the duality that he found is strongly coupled. It's strong duality, yet it leads to non-trivial consistency conditions because there is a sort of a cascade or a chain of dualities that you have to follow. So it seems that some examples are even richer than those that I presented. And his story obeys many consistency checks. It's really fascinating. Now, a summary. So there are robust quantum phases in 2+1 dimensions that involve emergent anyons, emergent topological filters. There are symmetry breaking patterns that are new. There are also more exotic possibilities, like the ones that I didn't discuss of Chang-Ha. It's not always a CFT. We have convincing evidence that it's not at large n. And weak strong duality is not always the case. There are also examples where there is new strong dualities, yet leading to non-trivial consistency conditions.
So went a bit over, so maybe one pressing question the most.
So can you describe the transition as some kind of a quotient of anyons?
A potion?
Quotient. Well, I want to use the word of condensation, but not quite right. But it's some construction of you get some anion from one side, some anion to the other side, combine them, then you quote them out.
The transition is a conformal filter, so it has gapless modes. It's not just a topological filter. But it does, but it does what you say. It does what you say. It's a weakly coupled conformal filter. So the transition is a weakly coupled conformal filter that on one side of the conformal filter has one set of anyons, and on the other side a different, sorry, this is not the right picture. On one side it has one set of anyons, and on the other side a different set. On the one side one set of anyons, and on the other side a different set of anyons. So it's a conformal filter that interpolates between two different topological filters. Now, I guess you're asking if you can think about it as a fusion of these two different sets of anyons or something?
Well, I can be very concrete. I have a paper that you quant post
Sure, guys, I think we're getting let's
well,
have
I
a
don't know. I have
session
to think about it.
We've got to get going. So I think Kerman is next, right? So thank you. So let's thank Zohar again.